Welcome to this first lecture of EE404 of this week. In the last lecture, we have completed the topic of phase plane analysis, and in the last lecture also, we started with the so-called limit cycles. And in this lecture, we are going to actually develop some theory on limit cycles and their non-existence or their existence. So today's topic is going to be the results on the existence and non-existence of limit cycles. On the existence and non-existence of periodic trajectories / limit cycles. So the general theory is developed for periodic trajectories. But we can of course think about their specific cases, limit cycles, with the same theory. So remember, not all periodic trajectories are limit cycles, but limit cycles are all periodic trajectories. So in this part of the course, we're going to see three results. These results are called as Bendixson's theorem. The second result is called index theorem. And the last result is called Poincaré-Bendixson's theorem. Okay, so we have these three results, and the first two of these results are giving conditions for the non-existence of limit cycles, and the last result is giving us some conditions for the existence of limit cycles. So I can say that the first two theorems are kind of negative theorems. They are predicting the non-existence. They are telling us only the non-existence of the limit cycles or periodic trajectories, and the last one is a positive kind of theorem. It can be used to predict the existence of limit cycles. So we are going to start with the Bendixson's theorem now. So I can actually start here. And the Bendixson's, before giving the theorem, I am actually going to be talking about some theorem that you have seen before in calculus and also in electromagnetic theory courses. So this theorem that we are going to see is called the divergence theorem. So you might remember this, and we're going to see this theorem in 3D first, then I'm going to try to present the 1D versions of the same 1D and 2D versions of the same theorem. So let us say that S is a surface. Let us say S is a closed surface in R cube. Okay? And let us say that V is the volume enclosed by that surface, by the surface S. All right? So here what we mean is that, suppose that we are in 3D, and this is my X, Y, and Z axis. So this surface S, I will draw here something like a sphere. It's going to be looking like this, and this is my surface S, and the volume enclosed by S is called V. Okay, and in this 3D, I will define a field f of x, y, z. In 3D, this has three scalar valued functions: f1 x, y, z, f2 and f3. So we have our field given like this. So this is the field. And what is this? At each point in the space, this is going to give me a vector. Okay? Just as our two-dimensional fields in the nonlinear second-order systems. So at each point x, y, z, this field is going to give us a three-dimensional vector anywhere on this in this space. And I will here write the divergence theorem for 3D. But before that, let me try to define some vectors. N is going to be the unit vector in the normal direction. To the surface. So this n vector is also having 3 components, n1, n2, n3, each one of them being a function of x, y, z. Okay? And I'm considering that these vectors are nothing but some unit vectors. Their norms are all 1, their magnitudes are all 1, and they are pointing orthogonal, they are perpendicular to this surface. So obviously at each point on this surface I would have a different n vector. All right, and he is here pointing outside to the surface, and it is in that direction. Here it is in that direction, etc. Okay, if I take an n here, it's going to be pointing in that direction. All right. So let us also define what we mean by divergence of f. Divergence of f is the scalar function, scalar valued function, which is defined as del f1 over del x plus del f2 over del y plus del f3 over del z. Okay? This is called the divergence. Sorry. Of f. So this is a scalar function, scalar valued function. It takes x, y, z, and it gives us this scalar quantity. Now we're ready to actually define our theorem. So the divergence theorem in 3D can be written like this. So I have S, and I have f dot product n ds is equal to integral over v divergence of f times dv. All right? This is the divergence theorem in 3D. So now let me try to explain these terms here one by one. So this is an integral over the surface S. So this is in general two-dimensional or double integral here. And I am integrating a scalar quantity. This f dot n is nothing but an inner product, or it is as you might call a dot product. Okay? So I take the dot product of f and n. That gives me a scalar at each point on the surface, and then I sum all of those scalars. Okay? And what is f dot n? It is magnitude of f times magnitude of n, and times the angle between these two vectors. I have said that n is the unit vector. As a result, its magnitude is 1. So this is nothing but magnitude of f times cosine theta. All right? So if I show the vector f at each point on the surface, let us say f is pointing in this direction at that point on the surface, and this is the angle theta. What we are doing is nothing but I'm separating this is my f. I'm separating this f into two components. The first component is along the normal vector at that point, and the other component, it is actually tangential to the surface. All right? And we know that the length of this component along the surface normal would be f times magnitude of f times cosine theta. Okay? So we are actually taking the magnitude of the component along the normal vector of this field F. I do the same thing for every point. So suppose that maybe F points in this direction here, then what I do is that I actually take its two components, the component along the normal vector and component orthogonal to the normal vector, and I take the length of this vector along the component of the component along the normal vector. That is what this F cosine theta would tell me. So actually here we are counting the vectors F along the over the surface in the direction normal to the surface. Okay. So and if an F vector is exactly orthogonal to the surface normal there, then cosine theta would be cosine 90, which is equal to 0. In that case, in this integral, I would integrate the 0 value. All right? So we are taking these projections onto the normal vectors, and then we sum all of these values over the surface. That is what this first integral would represent. And remember, sometimes we call this integral as the flux. Okay? Flux is the field, and the number of, in some way it's representing the number of vectors going outside this surface in the field F. Okay? And this integral is equal to another integral in the divergence theorem, and that second integral is the integral of the divergence. This quantity, integral of this quantity over the volume enclosed by this surface. Okay? That is my second integral. And the divergence theorem tells us that these two integrals should be equal. All right? So now this is the classical divergence theorem that we all learn in 3D, in calculus, maybe in physics, maybe in electromagnetic theory. Now what I'm going to do is that I will try to show you what divergence theorem would mean in 1D or in 2D. And in this course, we are going to be using divergence theorem in 2D because we are considering second order nonlinear systems where this field F is two-dimensional. Okay? But the first thing that I'm going to do is maybe more enjoyable. Let us look at divergence theorem in 1D. In 1D. So obviously, in order to be able to write this theorem in 1D, I need to define my surface and I need to define my volume. So we are on a one-dimensional space. Let us say that it's X. And in that one-dimensional space, our field would be just f of x. This is our field, scalar valued function of a real number. That is our field, because in 1D, this f vector will have only a single component, and it's a function of only x. So we would have just this part. All right? And what about the divergence there? Then the divergence of f would be only this part of this divergence in 1D, and that would be del f over del x. So I have a function f defined on this space here, and the derivative of that function is the divergence of that function or of that field. So if I define a volume in this 1D space, a volume would be just an interval. Okay? This is my V in the 1D space. And what about the surface of that volume? The surface is only composed of 2 points, A and B. And these are actually forming our surface S. All right? So now let us try to write this integral on the right-hand side of the divergence theorem. So it is not really difficult in that case. So if I would like to write V, the divergence of F, and I have dV here. This is going to be integral. Remember, in 3D, this was a triple integral. In this case, it's just going to be a single integral like this. And then I would have here the divergence, del F over del X. Instead of dV, I'm going to put just dx here, 1D component. Remember, this is the volume element. In 3 dimensions, this would have been dx, dy, dz, etc. And here we have the volume element, which is only given by dx to us. And I need to integrate this divergence over the whole volume. But that means that I need to put integration limits from A to B here. Okay? So I am integrating the divergence of F over this volume. All right? Now let me try to write the second integral as well. Sorry, the first integral on the left-hand side. It is S, and I have F dot N ds. Okay? So here my surface is just is composed of just 2 points. Okay? So this integral is actually going to turn into a summation in that case. An integral, as you all know, is actually intuitively it is a summation, and here it is that surface. Since that surface is just composed of 2 points, I will sum 2 numbers here instead of this integral. So here the value of the function, value of the field f at this surface point is going to be f of a, and the value of the field f at this surface point would be f of b. What about the normal vectors? The normal vectors would be pointing towards outside the surface. So the normal vectors would be shown like this. In this case, the vectors are still scalars. They are one-dimensional. That means that this normal vector is going to be pointing in that direction. Let us call that normal vector +1. Okay? And this one, since this is pointing to into the other direction, I will call this n bar as an arrow as -1. Okay? And then I need to take the dot product of f and n. But the f is scalar and n is scalar. That means that dot product should also turn into the standard multiplication in that case. But that is going to give me f of a times the normal vector -1 plus sorry, I'm writing into the wrong place. So that is going to be f of a times -1 plus, I'm thinking that this integral turns into a summation, then that is giving me f of a times -1 plus f of b times the normal vector there, which is +1. Okay? But you see that this is nothing but fb minus fa. Okay? And the divergence theorem in 1D is saying to us that these 2 integrals should be equal. These 2 should be equal, therefore the right-hand side should be equal. Okay? So I have ab del f over del x dx is equal to fb minus fa. All right? But isn't this obvious? So if I take the integral of the derivative of f, I would get f. If I evaluate it at the boundaries of the integral, limits of the integral, then I would get fb minus fa. Okay? So this is nothing but the fundamental theorem of calculus. But fundamental theorem of calculus is really some version of fundamental theorem of calculus. And we see here that this three-dimensional divergence theorem in 1D is nothing but the fundamental theorem of calculus in 1D. And therefore, I can actually say that the divergence theorem there is the generalization of the fundamental theorem of calculus to 3D. All right? And actually in 3D we might have many generalizations of the fundamental theorem of calculus and other vector field theorems like Stokes' theorem or other theorems that you might think of here that I cannot remember here. They are also the generalization of the fundamental theorem of calculus to the vector case. But here we're considering this generalization, which is the standard divergence theorem. So this is the divergence theorem in 1D. And now we're coming to the important point. We are going to come to divergence theorem in 2D, which is what we're going to use in this course. In 2D. In this case, let us try to visualize our scenario. So I have a 2D space here, composed of only the xy plane. And in this case, instead of a surface, I would have a curve. Okay? This is the curve C here, all right? And instead of the volume, I would have an area enclosed by that curve. All right? Encircled by that curve. Now I would like to think about the normal vectors. I know that I can define normal vectors at each point of this curve, pointing towards outside of the curve. So I would have normal vector here like this. And in this case, my f would be a two-dimensional vector, two-dimensional field, f1 of xy and f2 of xy. Okay? And the normal vectors would also be two-dimensional unit vectors. And here I can write this, then the divergence theorem quite easily. The dot product of f and n integrated over this curve C would be equal to the integral over this area of the divergence of f, dA. And what is the divergence of f in this case? We have this vector field, del f1 over del x plus del f2 over del y. All right? So that is what we are going to use in this course. So we see that when we have a vector field and when we have a curve C, then the outward flux over from that area would be equal to the integral of the divergence of f over the area A. All right? So now we are actually ready to be using this theorem in nonlinear system theory or nonlinear control theory. So let us say that, consider the nonlinear system represented by, so we have the system x dot is equal to f of x. We are always going to be assuming that this is a second order system, and that means that this f of x is nothing but a vector with two elements, two functions of two arguments. Okay? So we have this one. And we know that this f of x represents the velocity vector. Velocity vector at x. Okay? And you might guess that that is what we are going to choose as our f in the divergence theorem in 2D. So suppose that the system has a periodic trajectory. In the phase plane. What does that mean? Phase plane is just our x1, x2 plane. And we are assuming that the system has a periodic trajectory on that. So it has a closed contour like trajectory like this. Okay? So now I will talk about the velocity vectors on that periodic trajectory. We here assume that we have a periodic trajectory, and how can you find on that periodic trajectory the velocity vectors, these f vectors, by looking at that periodic trajectory? So for example, when I look at this point on this periodic trajectory, can f point like this? Point into that direction. Can f be like this at that point on the trajectory? So clearly f cannot point in that direction. Why is that? Because we know that the system actually moves like this. If f points in that direction, the trajectory should have moved directly in that direction. That means that f really on this curve, at this point, the velocity vector f or the velocity field f cannot point in that direction. So in which direction do you think f can point here? So here, there is one thing that you need to know. If you have a system, x dot is equal to f of x1, f of x, and if you have an arbitrary trajectory of that system in the phase plane, then when you look at a point, when you locate a point on that trajectory, the velocity vector would always be tangential to the trajectory. Okay? So for any trajectory of a nonlinear system, when you draw that trajectory and when you look at the velocity vectors at each point on that trajectory, if you draw those velocity vectors would always be tangential to the trajectory. Okay? So they would be pointing in these directions, but they would be tangential to the trajectory. Okay? So on this trajectory, if I look at my f vectors on that trajectory, those f vectors would be tangential to the curve here. Okay? So f would be pointing like this. Of course, the magnitudes can be different. F is here like this. F is pointing tangential in that direction like this. Here it would point like this, and here it might point like this, etc. All right? So on this periodic trajectory, I know all of the velocity vectors. If I find the tangential vector to that trajectory, I would know what my f is there, exactly on that periodic trajectory. So here is what I'm going to do. I'm going to apply the divergence theorem in 2D to that scenario. For that, I need to choose a curve, and I need to choose an area enclosed by that curve. So I am going to choose my curve exactly on top of this periodic trajectory. Okay? That is going to be my C, curve C here. Okay? So this is the curve C, and the area enclosed by it is going to be my A. Now I'm going to apply divergence theorem to that curve C here. Okay? For that, I need to know the normal vectors, or unit normal vectors to to that curve. But those normal vectors, they would be orthogonal to the curve, okay, at each point. This is my n, and at this point it's going to be orthogonal. This is n, and at this point it's going to be orthogonal n, etc. Okay? At this point it's going to be orthogonal and then pointing like this. But there is a very, very important thing there. You see that these f vectors, they are tangential. N vectors, they are orthogonal to the curve. So that means that between f and n, at each point on this curve C, these vectors are orthogonal. Between f and n, there is the angle 90 degrees. Okay? So on this curve, which corresponds to a periodic trajectory of the system, the field vectors f, they are the velocity vectors, they are always orthogonal to the normal vectors. Okay? So here, therefore here, on this curve C, on C, what is f dot n? What is the dot product of the velocity vector field and the normal vector field? In that case, because of this 90 degrees, I would have a cosine 90 here, which is going to give me 0. Okay? So then what does this mean in terms of the divergence theorem? For this integral is only thinking about points on C and summing these scalars here. So since all of these scalars are exactly equal to 0 on C, this integral is going to be equal to 0. Okay? So I would have C f dot n dc is equal to 0. What does that mean for the second integral? The second integral should be equal to the first integral, and that means that by the divergence theorem, the second integral should be equal to 0 as well. That means that the integral over A here, divergence of A, dA, is equal to 0. Okay? And what is divergence of A? Divergence of F is here, del F1 over del X1 plus del F2 over del X2. Okay? Here, instead of variables X and Y, we just have X1 and X2. So that tells us something very, very important. If we have a periodic trajectory of a nonlinear system, I have a periodic trajectory of a nonlinear system. If I integrate divergence of F over the area enclosed by that periodic trajectory, the result should always be equal to 0. Okay? So that is our important conclusion. If we have a periodic trajectory of a second order nonlinear system, if I calculate the divergence of F from the system equations, and if I integrate that divergence of F over the area enclosed by that periodic trajectory, the resulting integral should give me 0. Okay? So let us try to write this. If the system x dot is equal to f of x has a periodic trajectory, in the phase plane, then the integral of divergence of f over the area enclosed or encircled by the periodic trajectory is 0. Okay? So this is going to be actually what we're going to base the Bendixson theorem on. So what does this statement tells us? If there exists a periodic trajectory, then del divergence of f dA is equal to 0, where in the area, over the area encircled, let us say, by the periodic trajectory. Okay? So this statement is just a mathematical statement given like this. If there exists a periodic trajectory, then this integral is going to be equal to 0 over the area encircled by that periodic trajectory. So how can I use to actually predict the existence or non-existence of limit cycles or periodic trajectories? How can I use this statement to predict or to rule out periodic trajectories of a nonlinear system? So what do we want to do here? So we are going to be given these equations, and suppose that we really do not want to draw its trajectories, okay? We do not want to use a computer to draw the trajectories, or even if we use a computer, we do not know which initial conditions that we need to use to get a periodic trajectory, okay? So in general, what we want to do, we want to, given a system equation, we would like to predict that there is a limit cycle or there is a periodic trajectory of the system, or we would like to say that there is definitely no periodic trajectory of the system with those given equations, okay? So here the question is, how can I use this type of fact in order to be able to do either one? So I want to either predict a periodic trajectory, or I want to rule out rule out a periodic trajectory, meaning that there cannot be a periodic trajectory. Okay? So here, this type of statement, we will not be able to use this statement to actually predict the existence of a periodic trajectory. Why is that? Because this statement already assumes that there exists a periodic trajectory, and it implies something like this. So I have here a statement like P implies Q. So in this course, I will pay specific attention to this type of logical statements and what these type of logical statements might imply. So this P is the statement there exists a periodic trajectory statement, and Q is the statement related to the integral. Okay? So now I'm going to write the equivalent of this statement. We all know that such an implication would be equivalent to the following. If I have Q complement, then this implies P complement. Okay? What does that mean? So these two statements are equivalent. That would tell me that if I can make sure that over an area, if I can make sure that this integral is never 0, then I can be sure that there is no periodic trajectory over that area. Okay? If I can make Q complement, if we make sure that this integral is always non-zero, then that implies that there is no periodic trajectory, which is P complement. Okay? So that is how we can use this theorem. Okay? Suppose that divergence of f is positive everywhere. Okay? Suppose that divergence of f is positive everywhere in the phase plane. In that case, I definitely know that this integral cannot be equal to 0. Because divergence of f is always, if it is always positive, if I integrate it over any area, the result would be always positive. Okay? in that case, I can actually say that this integral is always non-zero, meaning that there cannot be a periodic trajectory anywhere in the phase plane. That is an argument which is actually similar to the Bendixson's theorem. So now we are ready to write the Bendixson's theorem. So I will first write the statement of the theorem, and then I will try to explain its components. So Bendixson's theorem is a sufficient condition for the non-existence of the periodic trajectories. Well, let us say, let D be a simply connected domain. Simply connected domain. I will explain what this is after the statement of the theorem. In the phase plane, the system x1 dot is equal to f1 x1 x2, x2 dot is equal to f2 x1 x2, has no periodic trajectories. In D, if divergence of f del f1 over del x1 plus del f2 over del x2 is not identically zero over any subdomain of D, and it does not change sign in D. Okay? So this is the Bendixson's theorem. And it's a sufficient condition for the non-existence of the periodic trajectories. You can say that, you cannot say that using Bendixson's theorem, you cannot predict the existence of a periodic trajectory, but you can predict the non-existence, all right? So here let us try to explain the statement of the theorem. Let D be a simply connected domain. So in mathematics, we have domain is an open set. Okay? So if I have the phase plane like this, then I'm thinking about an open set like this, D. All right? Domain is any open set in the phase plane. And I have here something called simply connected domain. Okay? Let me write what that means. Simply connected means having no holes. Having no holes. So of course I can think about different open sets here. So this is another open set. So this is my D, and let us say this is D1, and let us say this is D2. Okay? Both of them are open sets. Okay? So here the area enclosed by this curve here, this D1, it's a domain, and D2 is also an open set. It doesn't contain the boundary. D2 is also an open set, but only one of them is simply connected. Okay, so this D1 is simply connected, and D2 is not simply connected. Why? Because D2 has a hole in it. Okay, so here, simply connected domain means an open set which doesn't contain any holes in it. Okay, so I have D1 is simply connected, and D2 is not simply connected. Okay? So having the two open sets, we can make a distinction by checking if there are holes or not in the open set. And the ones having holes are not simply connected, and the ones without any holes, they are called simply connected. So what else needs to be explained here? So this is a simply connected domain in the phase plane. We are given the system, and the theorem statement tells us that the system has no periodic trajectories if this divergence is not identically zero over any subdomain is a subset of any domain which is also a domain itself. Okay? So a subdomain is nothing but I have a domain like this that is D1. Then a subdomain of this would be a subset in this, which is another domain. Okay, so here let us say D2 is the second set here. D2 is a subdomain of D1. All right. So the theorem says that if this divergence is not identically zero over any subdomain of D, we are given a D, and if divergence is non-zero over any subdomain in this D, and if it does not change sign in D, so if the divergence has always the same sign, and if it is not identically zero over any subdomain, then the Bendixson's theorem tells us that in D1 there cannot be any periodic trajectories of the system. Okay? So in D1 there cannot be any periodic trajectories if these conditions are satisfied. So now let us look at an example. We are given the following system: x1 dot is equal to x1 plus x2 minus x1 x2 square. And I have x2 dot is equal to minus x1 minus x1 square x2. So we need to here show that the system does not have any periodic trajectories. Any periodic trajectories in the region x1 square plus x2 square smaller than 1. Okay? So that looks like a task that we can attack using the Bendixson's theorem. So now let us look at the conditions. So first of all, this is this region, is it a domain or not? So when I look at the x1, x2 plane, I see that this region is covering the inside of a circle. It is the unit circle here, okay? And I see that this is an open set, so it is this region here. And it doesn't have any holes in it. That means that this region is actually a domain, okay? So this holds, and since it doesn't have any holes in it, it is a simply connected domain, okay? So we see here that this condition holds. Let D be a simply connected domain in the phase plane. This is going to be our region D, simply connected domain D. And now let us look at the divergence of F here. This is my F1, this is my F2. Let us calculate the divergence of F. Del F here is equal to, I will take the derivative of this one with respect to x1. It is going to be 1 due to this, minus x2 square, and plus derivative of this thing with respect to x2, and that would be give me minus x1 square. So this is my divergence, all right? Here, a thing that I would like to show you is that the Bendixson theorem would give us really a lot of idea about what the system can have. Suppose that is my divergence. What type of modifications that I can do on this system such that my divergence would remain the same? What type of modifications can I make on this system such that the divergence would remain exactly the same? In that case, it is really simple, because this is nothing but del f1 over del x1 plus del f2 over del x2. That means that for the divergence, only the dependence of f1 onto x1 is important, okay? Any function of x2 on the right-hand side really does not change anything. That means that into this system, I can add any function. Let me say not f, but let us say g1 of x2. I can add here any function of x2, and the divergence would still not change, okay? Because here we are taking the derivative with respect to x1. The derivative of this thing with respect to x1 would be exactly equal to 0. Similarly, in the second equation, I can have any function of x1 here, okay? And the derivative of this thing with respect to x2 would always give me 0. That means that I can make these additions, and the conclusions of this example would remain the same, okay? So now let us look at this divergence, the behavior of the divergence inside this region D, represented by this. So I see here that 1 minus, so by the way, this is wrong, of course. So I would have here x1 square. So you see here that this divergence is given by del f is equal to 1 minus x1 square minus x2 square. In the region D, I know that this quantity is always smaller than 1, meaning that this quantity is always strictly larger than 0 in D. Okay? Then what does this mean? I see that D is a simply connected domain, and I see that the divergence is not 0 over any subdomain of D, and furthermore, it doesn't change sign in D. It is always positive. meaning that all of the conditions of the theorem would be satisfied. Okay? That means that we can use the theorem to conclude that no periodic trajectories in D. Okay? So we can say that there won't be any periodic trajectories wandering around in this domain. Okay? But of course there can be periodic trajectories which might go outside and then come back. But we know that there won't be any periodic trajectory completely inside this region. So I will have a final question. So here I see that if x1 square plus x2 square, if it is larger than 1, in that case, so this completes this example. And let me try to look at the following task. Let us look at the region. I will call this region as D2. And let us say that this region is represented by the following equations. x1 square plus x2 square, which is larger than 1. Okay? By using the Bendixson's theorem, can I conclude that in this region there won't be any periodic trajectories either? Why? Because if x1 square plus x2 square is larger than 1, then I know that this is going to be always negative in that region. It is not identically 0 over any subdomain, and it doesn't change sign in this region. Then can I conclude that in this region there won't be any periodic trajectories either? So let me try to look at this region D2. D2 is now going to be the outside the unit circle. So I would have just this. So D2 would be this region, okay, outside the unit circle. I have checked the divergence condition. The divergence being identically non-zero, not identically being 0, or not changing sign, the divergence condition holds for this region. But I did not check whether this first condition would hold or not. Okay? Is this region a domain? None of the boundaries are included here. Okay? So we see that this is an open set. None of the boundaries are included. That means that this is an open set, but is it simply connected? So this region, you see that it is the whole of the state space except the unit circle and inside the unit circle. Okay? I see that this region unfortunately has a hole in it. Okay? So although this region D2 is a domain, it is not a simply connected domain. That means that by using the Bendixson's theorem, I cannot make any conclusions about the existence of periodic trajectories in this region or not. Okay? So D2 is not simply connected. That means that no conclusions can be made. No conclusions can be made by Bendixson's theorem. Okay? So let us look at another example. In this example, I will consider the following system. x1 dot is equal to, let us say x2, x2 dot is equal to x1. In this case, I have the linear system, okay? And we're going to apply the Bendixson theorem to this system to check about the non-existence of the periodic trajectories. So now here, let us find the divergence. And here, I will take my region D as whole R2. Okay? R2 is an open set, and it doesn't contain any holes in it. So this is a simply connected domain. Okay? So now let us calculate the divergence. Del F is going to be derivative of this one with respect to x1. I see that del F1 over del x1, this is 0 for this case. And del F2 over del x2, this is completely 0. So you see that divergence is 0 everywhere in this region. All right? Then what can I say? Since divergence is equal to 0, there will be periodic trajectories. Can I say that? There will be periodic trajectories. Can I say this? So definitely not. This is completely against the mathematical logic of any theorem or anything. So here, what does the divergence theorem tell us? It is a statement like P implies Q. Okay? P is the conditions of the theorem. So D, simply connected domain. These are actually forming what P is. Simply connected domain. Del F is not equal to 0 over any subdomain. And del F does not change sign. Okay? And what about Q? No periodic trajectories in D. Okay? So this is the logical structure of the theorem. If anything is violated here, if we violate any conditions of the theorem, any of the conditions, then that would give me P complement. Okay? And do you think this statement is equivalent to P complement implies Q complement? So definitely not. If P complement holds, meaning that one of these conditions would not hold, then there is no such equivalence. Then the Q complement is not implied here. If we do not satisfy one of the conditions of this theorem, then we cannot make any conclusions about Q or Q complement holding. Okay? So since one of the conditions of the theorem is not satisfied here, this condition is not satisfied, we see that here, for this example, I cannot really make any conclusion about the existence or non-existence of periodic trajectories using Bendixson's theorem. Okay? So in this case, the correct answer for such a question would be no conclusions using Bendixson's theorem. Periodic trajectories may exist, may not exist. I don't know. I don't know using Bendixson's theorem. If I use other tools, I might try to understand what happens for that system, but using the Bendixson's theorem, it is just no conclusions. And actually, when you look at this system, it looks like this. X dot is equal to 0, 1, 1, 0, x. And if you find the eigenvalues of that A matrix, you would get the eigenvalues are plus and minus 1. Okay? Meaning that here we have a saddle point type of trajectories, there won't be any oscillations, so there won't be any periodic trajectories for such a system. And if you just change this example just a little bit, x1 dot is equal to x2, and x2 dot is equal to minus x1, the divergence would still remain the same, but in that case we would have center type of equilibrium point. So there would be oscillations. So you see that if the divergence is completely zero, I sometimes do not have any periodic trajectories, and I sometimes have definitely some periodic trajectories. That means that in this case, no conclusion can be made by using the Bendixson's theorem. You can only use other tools, like going into polar coordinates, or if the system is linear, finding eigenvalues, etc. Okay? You can only make conclusions using other tools. So the final thing that I would like to talk about would be the following. Suppose that I give you a domain, okay? Suppose that this is a domain that it's a simply connected domain in this case. And suppose that I give you the divergence of the system that you would like to consider. Okay? So this is the divergence of the system that you need to consider. And this is the domain that you would like to consider in the Bendixson's theorem. Can I apply the Bendixson's theorem or not? That is the question. Okay? For this divergence, for this simply connected domain, can I apply the Bendixson's theorem to say that there is no periodic trajectory in this domain? So for that, we obviously satisfy the simply connected domain condition here. Okay? This is a simply connected domain. Therefore, the conditions of the theorem for the domain or for this region, they are satisfied. What about the conditions for the divergence? The divergence of f is not identically zero over any subdomain. Is this condition satisfied or not? So if I try to draw this divergence, then it would have the following structure. So it would be just a ball type of curve here. This is my state space, and this is the divergence, that f. So I see that there is a point, so the divergence is everywhere positive, except for the origin. Okay? Divergence is exactly zero at this point. Del f is equal to 0. So do you think the conditions of the Bendixson's theorem would be satisfied for this divergence? For that, I am going to look at this. Divergence of f is not identically 0. If I remove this part of this statement, it is definitely not satisfied because it is 0 there. Okay? In the domain, there is a point where the divergence is exactly equal to 0. Okay? But the theorem would still have a continuation here. Is not identically 0 over any subdomain. Okay? I want the divergence to be non-zero over any subdomain. I see that this divergence is exactly equal to 0 at a single point. Okay? It is 0 at a single point. Is a single point a subdomain or not? That is the question that we have to answer here. Okay? So I give you a single point. Is this a subdomain or not? Or is this a domain? So a single point is just a point, and in terms of set theory, if you want to classify it as an open set or a closed set, it is not an open set. okay? That is, a single point is not a domain, okay? So in order to be able to understand this, you need to check the definitions of what the open set is and what a non-open set would be, okay? But you need to remember here, a single point like this is not an open set. It is a set composed of a single point, and that single point is its boundary, okay? And therefore, the set contains its boundary, which means it's a closed set, all right? So this is not a domain. A single point is not really a domain, which means that this condition would be still satisfied for that example. Because here, the divergence is only 0 at a point, and a set which is composed of a single point is not a subdomain of D, okay? So here, for that condition to be violated, the divergence should be 0 in an open set, open neighborhood here, okay? So here, being 0 only at a single point does not violate the divergence theorem, because that single point is not actually a subdomain of D. Similarly, if you have a divergence which is equal to 0 on a curve, okay? What does it mean? So suppose that you have a divergence which is equal to this, x1 minus x2 squared. It is positive everywhere, and I'm considering D equals to R2. So I see that this divergence is positive everywhere except on this line, x1, x2, okay? So this is the line, x1 equals to x2, and the divergence is 0 on this line. That f is equal to 0, and it is positive everywhere else, okay? Does this property, being 0 on this line, does it violate the condition of not being identically 0 over any subdomain? Here again, a line or any curve, any one-dimensional curve is really not a subdomain. Okay, it is not because it's not an open set. The points on this line form not an open set. They do not constitute an open set, which means that being 0 on this line really does not matter for the divergence theorem. The theorem still applies for these examples, okay? Because these divergences, they would be equal to 0 at some points in these domains, but the points or the sets on which they are equal to 0, they are not subdomains, okay? So we do not violate the conditions of the theorem by these divergences, meaning that the theorem would still be applicable. So here, there won't be any periodic trajectories in this part, and here, there won't be any periodic trajectories in R2. Okay? So when does the theorem, when is that condition violated? For example, I can actually think about this. So I'm making it up here. So let us say that this is my divergence, del f, and let us say that I would have x squared minus 1. I'm making it up here, so x2 squared, let us say minus 1 here. And it is 0 if x1 squared, x2 squared smaller than 1, and equal here, x1 squared plus x2 squared is larger than 1. Okay? If I have such a divergence, in that case, let me say that I'm looking at this region, x1 squared plus x2 squared, smaller than 4. Okay? Suppose that I'm looking at this region In that case, I have the x1, x2 plane. So here is my unit circle, and here is this region. So this is D, and I see that D, which is this region, is a simply connected domain, okay? And what about the divergence? Divergence is positive here, okay? If this condition is satisfied, it is always positive, and it is 0 in this unit circle, okay? In this case, finally, we violate the condition of the theorem. Because in this region, I see that the divergence is positive, but it is 0 in some region here. And in this 0 region, I can definitely select some open set, and this open set becomes a subdomain, and I see that over this subdomain the divergence is identically equal to 0. That means that for this example the theorem does not apply. We can make no conclusions. Or this inner circle, the unit circle, is actually a subdomain, and in that subdomain I see that the divergence is exactly equal to 0, and the theorem is violated. It is because this inner circle is an open set. Here, a single point or a single curve like this, one-dimensional curve like this, they do not constitute subdomains. The subdomains would be in the form of open sets, which you can have like this. All right? So actually, this completes the topic of divergence theorem, Bendixson's theorem, and we have the next topic, which is going to be the index theorem, which is going to be covered in the second lecture of this week, and we are going to continue with the third one afterwards. But that is going to be all for this lecture. Thank you very much for watching. Bye.